So hello, I'm Deborah, and I'm currently doing an internship at the Royal Observatory of Belgium, and therefore I thank the IMO to giving me the opportunity to deliver this talk about the radio meteoric observation using SPADE. So I just begin with a quick reminder of the forward scattering principle, which is the radio transmission principle we used for our SPADE project. How the principle where it was already defined before, which is to an easy definition of the thing, because we're using like a transmitter and a receiver in two different places, and the receiver is tuned to the frequency of the signal emitted by the transmitter. And when the meteor enters the Earth atmosphere, the signal can be reflected on the meteor trails and then received by the receiver. And in our case, we will use the BRAMS transmitter at the transmitter for this project, and SPADE, our SPADE antennas for the receiver part. So here you have a little pictures of our antenna for SPADE, which we will see on Saturday in the Humain Radio-Astronomy Station. It's configured like in a circle of 7 antennas with one in the middle, so it's 8 antennas. So SPADE stands for Small Phased-Array DEmonstrator. It's like for the SPADE thing, we'll combine the 8 signals received from each of antennas to give an output signal. We will then work on it. And then the range of our phased array is from 20 to 80 megahertz, and thus works perfectly for the frequency of the signal emitted by BRAMS, which is of 49.97 megahertz. And that's why we decided to try to observe meteors using this phased array. In our case, we are using 2 receivers, so we have to synchronize them using a reference clock, and for it we're using a GPS. And we're also using the technology of software-defined radio to process and combine our signals received from the 8 antennas. So for the first step of this radio meteor observation, we begin by made some little calculation of the power received. And then you have like a lovely diagram of a configuration, a really simple configuration of what is the situation of the BRAMS transmitter, the SPADE receiver, and the reflection points of a meteor trail. So you can see like some of the parameters we used, because we used like a simplified formula to calculate the power received, and we made also some assumption on several parameters. So all the first result we have are preliminary results and are not the precise one, but it's just to have a general idea of what we're doing and what we will receive in the first day. And you also have like the BRAMS and SPADE localization seen from above, just to have an idea of the spherical coordinate we used for it. The first thing we had to do was to choose one of the SPADE polarization, because each of our antennas has 2 polarization, which are geometrically oriented north-south and east-west. That's why we call this, we give them this name. And the first calcul we made was for a zenith configuration, so when the meteor is just above the receiver, and we calculate the difference between the east-west and the north-south polarization in terms of power received. And in the end, for like 3 different heights we choose, the power difference were almost of 3 dBs, which is twice the power. So we choose the north-south polarization for our first observation and our first test, and that's the polarization I will use for the next comparison we made. So you have a little thing which is the north-south polarization with the orange arrows, and I will show it on the Humain Radio-Astronomy Station on Saturday. Then, because we have a BRAMS interferometer in the Humain Radio-Astronomy Station, we find it interesting to compare the power received for the 2 only in terms of the antenna, so without any filters or amplifier, and for the zenith configuration also, because we find it interesting to have like the difference between the antennas we used, and therefore the differences in power is almost like 14 dBs difference. So it means that it seems that our SPADE configuration is more sensitive in this configuration than the BRAMS one, but these results will be then confirmed and observed when we will do the actual observation in the station. And then why we used like the zenith configuration for all the calculation and why we will use it for the first test we want to make is only because it's the easiest configuration we have. And it's the more sensitive one, because we made some also comparison with different elevation, as you can see, and we normalized the gain received by the antennas, and the zenith gain was much more important than the other two. And that's why we used the zenith configuration for all our calculation and for the first test we will made. You also have like the antennas patterns we simulated, and you can see the big red beam oriented to the zenith, and that's confirmed that what we had with our calculation. And we also calculate the 3 dB angle, which is of 21 degrees. It's a really narrow angle, but therefore it helps us to like avoid all the low elevation noise and interferences. So it's much more sensitive in this direction, and we have much more good results by avoiding all the human-made noise, which are on low elevation. And then for what we intend to do, it's really, really important for us to measure the electrical length of our antennas, because we need to manage the difference in phases of the different antennas. Indeed, the antennas are already installed in Humain, and the cable are probably not of the same length, and a difference in length can cause a difference in the phases received. And if we are not managing it, we can have an error after combining the signal for our output signal. So in order to have much more precise output signal and the right one, we need to measure the electrical length of our 8 cables, which we will be doing soon on site. And for measuring it, we are using what we call a vector network analyzer to do it. And you have an example of change of phase for a cable just on the left corner. And yeah, so we will do it soon, and with maybe a cable to do it, because the 2 cable extreme end of the thing are too far away to be measured like simply with just the VNA plugged in. And finally, for our receiver parts, we are using a USOP X30300, and our analog to digital converter is of 14 bits resolution. And because we don't have yet choose sample weights, we made some simple calculation of the total amount of data we could receive depending on the sampling weights. So we tried to calculate the total amount of data from the minimum sample weight we can use to the maximum one, and then we will choose the sample weights which meet our needs for this first experiment. And you also have an example of the software-defined radio software we're using, which is Meteor radio with all these block thing you plugged. And that's how we will process and combine our signals for the phased array radio observation of meteors. And that's it. Thank you.